I'm always doing it. I never am. Okay. See if the iPad joins. Come on, iPad. Okay. Well, while you guys get your thing set up, so we're gonna do reactants versus products. You are gonna need 10 items. You have 10 beans if you're in class. You're gonna pull 10 beans out of that cup. We're gonna illustrate this again because this was a concept that I didn't do well with when I learned it. So this is a good visual. We're gonna log into this again. Try to contain your excitement. All right. Max is about falling out of his chair over there. Okay. We're gonna trust. Doesn't work. Okay, bear with me. The iPad's being a little stubborn. You might witness me throwing it through a window. One day it's gonna happen, I think. Oh, the iPad joined. Okay. All right, let's go ahead. We're going to take a peek at Q versus K. Does anyone remember? I mean, I do have the information up here, but does anyone remember anything I said about Q versus K on Friday? You can drop it in the chat. It doesn't have to be anything sciencey, just anything in general that stuck out to you. Q versus K. At home people, you can drop it in the chat. In-person people, yeah, Marley, is that a raised hand I see? Okay.
Q is like a reaction, and A is like final state of it.
Yeah, so Q is like a moment in the reaction. I like the word moment. That's good. It's like a moment in time, and then K is at equilibrium. So K is when it's reached its happy point. Life's all about balance. And so yeah, Q is your moment in time, and K is that moment exactly at equilibrium. Yeah, Josie, they do use the same equation, so there's nothing different about our calculations. We just have to be aware of, like, are we at equilibrium or are we at just a certain moment in time? And so based on that moment in time, that'll tell us or help us predict which way the reaction is going to shift to try to balance itself back out or get back to equilibrium. So we looked at things this way through a couple of scenarios. So if you've got your beans, we're going to illustrate this part. If you have 10 random items at home that you'd like to sort between the circles, please feel free. But for our reaction, this imaginary reaction, we were at 3 products and 7 reactants. Nope, said that backwards. 3 reactants and 7 products at equilibrium. So our equilibrium value is 7/3, just the amount of things we're going to go with to keep it simple. And then this is 2.33 at equilibrium. Then what we did is we shifted 2 of these over here. So now I'm in this state. So I have shifted 2 of my products to the reactant side. So now I'm looking at this moment in time, this snapshot of my reaction. So we did Q, make that bigger. So we did Q is products over reactants again, and this time it's 5/5. You're going to remember K is 2.33. This is at equilibrium, and this is our moment in time right now. So Q is less than K. 1 is less than 2.33. So if Q is less than K, and I know to be at equilibrium, I have to have 3 dots over here and 7 dots over here. Which way do I have to shift my dots or my beans if you're using the beans? People at home, feel free to drop it in the chat. So this is my setup. How do I get back to equilibrium? What do I need to do? What am I going to shift? This is my moment in time. Yeah, that's green Sprite. Thomas, what do you want to do? We got to get back to 3 and 7. So where do you want to shift dots? Right now I'm 5 and 5. Yeah, so this reaction, I'd like to get back to equilibrium. So if it started here, if this was my moment in time to get back to my equilibrium state, these 2 guys need to go back over here. So my reaction, based on the initial state of 5 and 5, my reaction shifted back in the product direction. And that's always going to be the case if Q is less than K. You're going to always shift towards the products. In that case, so you've got basically too many reactants and you've got to convert a couple of them into products. So let's look at another scenario. If you have 1 kernel on the reactant side and 9 in the product tray. So if you're sorting beans, I'm going to set it up this way. So keeping in mind equilibrium, life's all about balance. Our happy place is 3 and 7, but right now I'm 1 and 9. So Q is going to be 9 over 1, products over reactants. That's 9. 9 is a whole lot bigger than my equilibrium number. So in this case, my moment in time, Q is bigger than K. Okay, so to get back to equilibrium, back to my happy place, life's all about balance. Max, what do you want to do? How do I get this moment in time to be back to 3 and 7? We're going to shift 2 of these guys back. And that gets me back to 3 and 7, which is equilibrium. So in this case, if Q is bigger than 7, I'm going to make a shift towards the reactant side. And that pattern will always hold true if Q is bigger than K. Since it's products over reactants, that means you have too many products. We got to convert some and send them back to the other side. What questions do we have about those 3 patterns? People at home, you can drop it in the chat. People in here, what questions do we have? Are we feeling generally okay? Not okay. Questions? General confusion and not confused. That's babbling to fill the silence. Okay. Okay, so let's take a peek then. Let's look at, we're gonna look at what this looks like in the terms of like numbers. Like what do we, like how's this gonna look like, you know, on an AP question, possibly. Okay, so this is what it could look like. So they have an equilibrium constant K they're gonna give you. So we've got 9.8 times 10 to the 5th. That's my happy place for equilibrium for this reaction. First thing I do always want to check though is that reaction balanced? Sometimes they are, sometimes they're not. So what do we think? Tristan, you were my balancer on Friday. You're online now. Hopefully you're there. I don't know. Are you? Yes, I think I saw you. Yeah, you are. Well, your little icon is. Okay, Tristan, is this thing balanced? You can drop it in the chat. Yes or no? Let's see if he's at his computer. I don't know. Yes, all caps. Thank you. Love that. Okay. So yeah, we are balanced, so we're all good there. Okay. So part A, it says find the reaction quotient. So that's just a fancy word for Q. So our moment in time, if we know we have these concentrations. Okay. So I have to think for a second. Sorry, it's going to happen a lot. All right, we're going to do products over reactants. So this is our product. So we're gonna put this guy on top, and we're gonna put this thing on the bottom. Does anyone know why I didn't include sulfur? Where's that? Where'd that go? Why is that not? Yes, Thomas. It's a solid. I don't care about it. Its concentration is not going to change, so we don't want that. Get out of here. Okay, so we just got to plug our numbers in. So somebody with a calculator, because I don't want to. I'm not mental mathing this one. 0.762. And Josie, watch my exponents. You're good at catching if I miss an exponent. I don't think I am though. Everything's got a 1 in front. So, and then we've got 0.483. Feel free to shout out a number. Drop it in the chat if you've got it. Oh, did I do it backwards? I do a lot of things. Yeah. Sorry. That's, I don't write things. I don't read very well sometimes. Products over reactants. What are you doing, Fitz? Come on. All right. Sorry. Flip that. Thank you, Josie. You're going to be my spotter. I'm going to get my key out just so that's where we're at. Okay. Yeah. Okay. All right. I'm going to check my key. All right. So we should get this. This is what I have on my key. Granted, it's not a key that I've made. So we do want to keep checking for mistakes. Okay. So this is my moment in time. This is my snapshot. This is where the reaction is at. This is the ratio of the products to the reactants. So here's what I have to look at. I need to compare this number to the K number that was provided. So is 0.634, is that bigger than or is that less than my K number? This is a positive exponent, 9.8 times 10 to the 5th. So bigger or less? What do you think, Marley? Yeah, thanks for raising your hand. It's a lot less. So what that tells me is my moment in time right now, like, so I have to decide, which way am I going to shift? So my moment in time tells me I don't have enough products. Hold on. Gotta think about it in my own brain. Yeah, I don't have enough products. So I'm going to have to shift in the product direction. So from my reactant side to my product side, if Q is less than K, then I'm going to shift in the product direction. Because what that's telling me right now is that I have a number less than 1, kind of like, so you got to think like products over reactants. So that means I have too many of these things, creating a decimal number. I'm dividing by a really big number, so I'm gonna have to shift in the other direction to get me more products. So when they say in which direction will we proceed, we're going to proceed in the product direction because Q is less than K. There's a lot to think about, evaluating those steps. So yeah, let's have it. Marley, what's your question? Yep, that's a good point. Let me write that. So if your snapshot or your moment in time, if Q happens to be equal to K, you would be at equilibrium. Like your moment you're measuring equilibrium would be at equilibrium. Just as a side note, yeah, we are not there. This one. But deciding on the shift, what questions do we have? Like kind of the logic. The other thing I always think of is this number is less than 1 too, which tells me I do have more reactants. So I'd have to then swap those into products. Any questions from people at home? This is a little bit, there's a lot of thinking. What questions? Drop them in the chat, or if you're feeling spicy, feel free to unmute and type in all caps. Any questions in here, or have I confused anybody yet? I can try to explain it different. I will not be offended if you are confused. Okay, let's try another one to evaluate things. We have this reaction. Tristan, you're gonna have to check if it's balanced. My balance checker. Hopefully you're still there. It's like a giant trust exercise in virtual learning. Are you there? Are you not? Okay, we have another equilibrium constant that we're given. And we want to check to make sure everything's balanced, first of all. So if it's not, we're going to have a bad time. So this one's a little bit of a doozy, but Tristan, is it balanced? Yes, all caps again. Yeah, it is balanced. One more checking there, but okay. So let's go ahead and take a peek. This one's not going to be as nice, because why would it be? AP Chem. Okay, so find the reaction quotients. We're going to find Q again, but this time they give us moles. They don't actually give us the concentrations. We're ramping it up a little. So we got a bunch of mole numbers here, and we have, of course, not a nice 1 liter container. So concentration again is big M is moles over liters. You probably thought when you were taking AP Chem, you didn't realize how much math there was going to be. But okay, so let's first of all just write our quotient. Write it out. Thomas, are there any parts we're going to ignore, or do we want to keep all the parts? We want to keep all the parts. Yeah, why do we want to keep all the parts? They're all gases, so their concentrations are going to change. And so we do care about that because that'll affect how our reactions do moving around. Now, watch me though, make sure I get these in the right spots. I got my exponent of 3. I got my little 3. Okay. So this is what I'm going to eventually fill in, but I'm going to have to find all of the concentrations of all of the things, which is a little pesky. But let's go ahead and give it a whirl. Okay, so we've got the concentration of H2O. We've got 0.02 moles over 2.5 liters. We're gonna need a number for that. CH4. Gonna go right down the list. 0.5 divided by 2.5. I need a number there. CH4. Need a number there. Did that one? What am I doing? Not that. I want H2. Sorry. I will check my numbers. I'm not a great reader, so 1.7 divided by 2.5. And CO 0.6 divided by 2.5. So if you guys get any of these at home on your calculator, put the numbers in the chat. Tell us what you get. I think I got them all in the right spot. Josie better check though. When I read things, I turn them around, so. If anybody has numbers in here, feel free to shout them out. Yeah, Marley, which ones do you have? Okay. So those are our concentrations. So you do have to watch your units. This one, they were all given in moles, and then they gave you what size container it was. So you had to convert them first into concentrations. Because Q with the little C by it tells you we're working with concentrations. So just keep that in mind. Okay, so now we got to plug and chug. So I'm not going to use parentheses. Okay, so we've got watch that, I put them in the right spots. 0.24 times 0.68 to the third power, all over 0.2 times 0.08. I cannot math that, so if anybody wants to put a number in the chat or shout it out loud, feel free to do that. Oh, I do have the key for this one. All right, we got, so I can check. I get 4.7, but put it in your calculators and make sure you get the same thing. This is what my key says. Again, I didn't make it. Okay, we got a couple people with 4.7, so either we're all wrong or we're all right, but at least we're doing it together. Okay, so 4.7. So that's part A. Any questions on part A? What questions might we have? Okay, if I go too fast, I get excited with math and I just kind of get on a roll. So stop me or shout at me or something, drop it in the chat, few questions. Okay, so 4.7, Marley, you already mentioned this. 4.7, is Q and 4.7 is K. So for question B, are we at equilibrium or are we not? Yeah, oh, you're nodding at me. Yes. Q is equal to K. So our little snapshot that we happen to take is already at equilibrium. So we don't need to like proceed in any direction to correct ourselves. Our reaction will just keep proceeding as it is right now because we are already at our happy balance. So we are at equilibrium. So no shifting because Q equals K. Any questions on that before we bounce to the next one? The next one I think is harder. I don't remember though. Ready to say some prayers. Any questions? Okay. Let's roll through another one here. Make sure this is one with it's not really any different, but technically so with gases are a little pesky. And so sometimes we measure gases instead of concentration, we measure them in terms of pressures because gases exert pressures all the time, that they're moving around really fast, and that's just kind of what happens. So we have what is called KP. So the P just meaning that we're measuring things in terms of pressures when we're looking at this one. And they're going to give us pressures. ATM is a pressure unit. So if you don't remember that, you want to remember it now. ATM is a pressure unit. So Tristan, is my equation balanced? I should probably actually check these and make sure he doesn't say yes, and then I just go with it. Tristan, is my equation balanced? You might say, yes, all caps. All right, great. It is balanced. I looked at it too. Okay, so we're good there. We want to find QP. So we're not going to use brackets because we're doing pressures, but it's still going to be set up the same way, products over reactants and using our exponents and stuff. So our notation to indicate we're doing pressures is going to look like this. It's like a big P and then a little subscripted thing of whatever it is you're describing. And if we had a coefficient in front, we would put a little exponent up here like we did on the K stuff, KC with concentrations, but everything's 1 in front. All our coefficients are 1 here, so I don't need to do that. But then my other product is CLF. And then on the bottom, I'm going to put my reactant, CLF3. And all those P's mean are just pressure. So we're just going to plug in the numbers they gave us because those are already in pressures, and we just have to do a plug and chug. So we've got 0.025 times 0.097. 0.632. Somebody divide that on a calculator. Does anyone have a number yet? If you have a number at home, feel free to drop it in the chat. Anybody in here get a number yet? Yeah, what'd you get? Okay. Yeah, that should be lower. Yeah, what'd you get? 0.00033. 383. Yeah, that's about right. Okay, so that's a tiny number. Oh, yeah, Kylie agrees. And thanks for, we don't actually need units on this because the units kind of cancel because we have ATMs on top, ATMs on the bottom. So the units kind of cancel out. So Q's and K's don't generally get units. They're just a ratio between your products and reactants. They don't require a unit. So that's that one. So now for part B, it says, will the partial pressure of ClF3 increase, decrease, or stay the same as we approach equilibrium? So let's decide first of all Q versus K. So are we greater than, less than, or equal? K was given up here. So is our Q value greater, less, or equal to? Harley, what do you think? Greater than, less than, this number versus that? Yeah, it's less than. Okay, so if it's less than, that means I have more products. Or sorry, I have more reactants. I've got more reactants than products because Q is a tiny number, which means the thing I'm dividing by must be a big number. That thing I'm dividing by, oh, thank you, Morgan, is going to be, so we have a lot of reactants. So that means my reaction is going to shift in the product direction. So it's like, whoa, I got too many reactants. I'm going to need to shove a couple of those things over on the product side to get me closer to equilibrium, to get me closer to that K value. So ClF3, they're going to be converted into products. So what do we think that would do to the pressure? Because it says the partial pressure of ClF3. So we're going to convert some and ship them over to the product side. How do you think that's going to affect the pressure here? Is it going to go up, down, stay the same? What are our thoughts? Feel free to drop them in the chat, people at home. Let me know you're still there. So we're converting some of these guys. So we're going to have less gas particles on the reactant side. So what do you think that would do to the pressure? What do you think, Thomas? Do you think the pressure would go up, down, stay the same? You think it would go down? I would agree. Why do you think the pressure would go down? Yeah, we have less particles. The gas particles are like the pesky little rebels of the chemical world. They just exert pressure and go in all sorts of random directions. And if we have less of them, we're going to have less pressure. I would describe Kanaji as a gas particle. The more Kanajis there are in a room, the higher my blood pressure goes. So, Trail, I hope you're still there listening. So less gas particles, so our pressure is going to go down. So you just have to decide what are we converting, and since those products or those reactants are being shipped off to the product side, that reduces the amount, which reduces the pressure. What questions do we have? How are we feeling about Q versus K? Come on in here. Any questions so far? Okay. I'm gonna set up a poll. You guys think about it if you have questions, and then I'm gonna set up a poll. Okay, so we are at a point. So, okay, I'm gonna launch a poll. People in here, you can just tell me. Or you can respond in the poll either way. Okay, so we're at a natural splitting point. I can give you some time to work on practice set 2, if in its entirety. So we've essentially covered everything on practice set 2 for you to do. So I can give you time to do that right now. Or we can move on to kind of the next topic, which we won't finish all of that today. I already planned for that, but which is ice tables, which is fairly mathy. You like algebra, you'll like those. So give me a vote just so I can kind of see, like, are you feeling to practice more right now instead of dump new stuff in your brain? Or, yeah, tell me your thoughts. People in here, what are you feeling? Would you like to practice more? Would you like do practice set 2 instead of jumping to a new topic? Or feel free to say it out loud if you want. Marley is indifferent. Okay, great. Max, how about you?
This is what you guys need.
Great. Is it Calvin? No. What is your name back there? You, yes, we just made eye contact. I'm trying to learn names. Oh God, what's your name? Yeah, Calvin. Your name's Calvin. Is it Calvin? What do you feel like doing? Okay. Indifferent. It's currently almost, it's like tied online. So people vote. Darlie, what do you want to do? Don't care. I'm not helping me. Everyone's indifferent. Thomas, what do you want to do? Thank you. You have practiced that too, right? Emma. Took me a second. You'd rather do practice that too. Capital, right? Yes. Do you want to do practice that too, or do you want to do the new topic? Huh? Okay, I do have one more. It sounds like you read my mind. Okay, so I can go over one more. That'd be fine. Ooh, I almost sucked out of meat. That was scary. Soraya. Oh, yes. Okay. Sorry, I'm learning names. What would you like to do? What are you feeling? Oh, you're also indifferent. Okay. Great. It's tied at home. All right. So let's do this. Let's check it in. Okay. Let's see. So we've got one more for this stuff. So let's do this, and then we will bop on along to an ice table example. We're gonna do that. Okay. Don't want that. Oh, I do want that. Okay, let's look at this one. Tristan, am I balanced? I need to see if I balance first. Okay, let's check and see. Tristan is the equation. Yes, thank you. All caps. Love it. I can feel your excitement. It's almost like you're in the room. Okay. We are balanced. Yep, we are. Okay, I just want to check myself. Okay, so let's do one more of these, and then we'll bop on along to an ice table example. I don't know how many of those you're going to want me to do because they're a little bit extensive, but we'll at least get through one just so you can kind of see what they're all about. Okay, so we got this reaction. So we're going to talk about stress. Will stress increase or decrease the reaction quotient Q? So there's no numbers on this one, but we just have to kind of think logically. So here's what's happening. So sometimes life happens and just dumps some stuff on you, kind of like 2020. Too soon? Okay. So suppose some additional CO is added to this system. So we're going to dump in more of that stuff. We're going to dump in more of that gas. It's like we're going to put more Kanajis in the room. What's going to happen? So what we want to think about is, will we increase or decrease the reaction quotient? So remember, reaction quotient is products, Q is products over reactants. So CO, is that a product or is that a reactant? Max, is CO a product or a reactant? It sure is. So we're gonna write that down. So CO is a reactant. Cool. Okay. So if I dump in a bunch more of that, what do you think is going to happen to this ratio? Is it so we're adding more to the bottom? You think it's going to get bigger or smaller? We're going to increase the bottom number. That's going to get bigger. So what's that going to do to the overall number? Yeah, so Josie, you said decrease. What are your thoughts behind that? So Josie thinks that the ratio, if the bottom number gets bigger, the overall fraction here, the answer is going to be smaller than it was before. Why do you say that? Great. So you're just plugging in some numbers. So yeah, I like that. So let's say I'm gonna use your example. So like she just plugged in some numbers and tested it. When in doubt, test it out. So 9/9 is 1. And then so versus like 9/3 is 3. So if I increase the bottom number, dividing by a bigger number, so that's gonna reduce my final answer. So since CO is a reactant, we're just gonna basically explain what we just tested out. We're gonna increase the reactants, which are in the denominator. So we have more reactants than products. So P divided by R, products divided by reactants. Q is going to decrease. So it's going to get smaller. You kind of have to think really mathematically about what you're dividing. So which direction, if I just dump in a bunch of stuff, if I dump a bunch of Kanaji Thompsons in one room, my blood pressure will go up. What am I going to want to do with those Kanajis? Am I going to keep them in the room, or am I going to go send them somewhere else? So part B is asking, which direction will the reaction shift when I dump in a bunch of stuff on this side? Do you think it's going to keep it all there, or do you think we're going to have to like move some of it to the product side? Yeah, Marley, what do you think? Yeah, we're going to have to move it to the product side. Why do you think? Yeah, it's like we have too many reactants. So we're going to convert some of them into products. So, if it was a bunch of Kanaji gas particles in a room, keep my blood pressure down, we got to ship them out of here. Okay, now part C, will the rate of the forward reaction exceed the rate of the reverse reaction before equilibrium is reestablished? So we're going to move from the, we're going to speed up we're going to make more products because we dumped in a bunch of reactants. That's going to offset my balance. I'm going to have to make some products out of that. So for this one, since we're moving in the product direction, the forward reaction, we're going in the traditional, like dumped in products, reactants, I got to make products. So the forward reaction is going to move faster. Rate will increase, we can say. For part C. So you want to think about which way am I shifting the reaction towards the product. So that's the forward direction, the traditional reaction direction that's going to have to speed up to get me back to equilibrium. And then for part D, when equilibrium is reestablished, will Q be greater than, less than, or equal to? So now I'm at equilibrium and I take a snapshot. So what do you guys think? Is Q going to be, that's when I reestablished equilibrium? Marley, you've already kind of answered this. Am I going to be greater than, equal to, or less? We're at equilibrium. So my snapshot, so we're saying like, okay, our moment in time, we're back at equilibrium. So is Q is my moment in time. And I always compare it to equilibrium, but I'm at equilibrium. They're just going to be equal to each other, yep. Okay, so that's a non-mathy example. That's just kind of thinking through what's happening at the various points, just like in a non-number sense. So what questions do you guys have on this one? Anything here before we try an ice table? What questions do we have? You guys are troopers. There's a lot of math today. Thanks. Any questions for people at home? Feel free to drop them in the chat. Okay, so let me pull up, what is today? Oh, ice tables. Okay, I'm gonna pull up the next set here. We're gonna look at, not that, we're gonna look at what's called an ice table. So there are a series of steps that we do for this. So I would take a moment. Step one is Tristan, right? The balanced equation. So take a second here and get a couple of these steps written down, and then I'm going to do a couple of examples to explain what on earth these steps even mean. We'll probably get through one of these today, and then whatever we don't finish, we'll finish Wednesday. And then the rest of the time will be yours to practice on Wednesday for the ICE problems. Initial change, and I can't remember for the life of me what E stands for. Pull this up on the iPad. Right, it cooperates. So really big. Okay, so ICE tables kind of relate back to Q and K. It's gonna help us, we have to use Q to decide which way something's gonna shift. So it's gonna be a way for us to like find concentrations of different things or what concentrations might be needed at various points in the reaction, based on kind of what's going on. And so we'll always have to have a gauge on what equilibrium is and where Q is at. So like what snapshot or moment in time are we at to decide which way things are going to shift. Steps, we have to write steps. These are a little algebra heavy, so I will preface that. We're going to have an X. We're going to have to solve for an X at some point. Brace yourselves. But here's the general process. So this is ICE, again, stands for initial, and then change, and can't remember what E stands for. I think equilibrium maybe, but basically you've got where your reaction's starting at, you're predicting what change might happen, and then you're trying to use that to find some missing information, essentially. So we're going to kind of string all the parts together. So always make sure your equation is balanced. If it's not, you're going to have the wrong equilibrium expression. You're going to have a bad time. So you're going to make sure it's balanced. You're going to write K. You're going to want to write your equilibrium expression. And then we have to calculate what moment in time we're at. Because it's not going to always be at equilibrium. We have to figure out where we are. So we'll have to do some calculating with Q to figure out like where things are at potentially. And then we'll have to talk about which way we think things will shift based on what Q is. You don't always have to do this. It's only in certain problems depending on what's given to us. So we're gonna use the first example today. Say a few prayers for Mrs. Fitz, so this has been a hot second. But we're gonna use a straightforward one. So an ICE table, I'm gonna show you how to do that. It's basically your reaction in various steps. And then we're gonna have to solve for some sort of unknown. And we're going to use, once we have our unknown, we'll find various concentrations of each of our items in our reaction. So that's kind of our process. And I'm going to put, I've got the steps here again on each of my slides. So these are the same. If you don't have all these written down yet, they are here. I'm also recording this. So what time do we get out of here? Yeah, we're going to be cutting it close. So that's okay. We've got Wednesday. So Tristan, is this equation balanced? You got a whole lot going on here. A little combustion thing, maybe. I think we're balanced. I feel like we are. Yep, we're balanced. Okay. So we've got a reaction here. To set up my ICE table, we're just going to get into the basics of this right now. You're going to organize your reactants, products, and things basically into columns and rows. So we're going to be hopefully given some sort of initial value. We're going to have to decide which way the reaction shifts and what kind of change is going to happen, and then what we're left over with. If my explanation for this sucks a little today, I will make sure it's better by Wednesday, because this has been a hot second for me. So, okay, so we've got a few things. So we have a balanced equation, check. We got to write our equilibrium expression. So let's do that. So at equilibrium, these are the things we're putting together. Okay, and then we have to look at what numbers they give us, and we're not at equilibrium right now, so they are going to tell us that at equilibrium, K is 5.10, so we do have that number, but, oh yeah, okay, so we've got 1 mole of everything in a 1 liter flask, so this one's pretty straightforward. We have to get, based on what they give us, we have to calculate Q. So where are we at? Like, what's our moment in time? So since everything's 1 mole in 1 liter, the concentration of everything's going to be 1. So that's kind of nice. Thank you, person that made this key, for making the first one easy. So Q is going to be 1. So we have to decide right now. We've got K given. We have a Q value. 1 is 1 less than, equal to, or greater than 5.1. Q, where are we at? 1 is, was it greater than, less than? Thomas, what am I putting in here? What symbol? Is 1 greater than or less than 5.1? It sure is. Alligator always eats the bigger number. Okay. So we have Q is less than K. Seems like a popular thing here. Which way is my reaction going to shift? Is it going to shift towards the products or the reactants? Q is less than K. Any thoughts? Don't all jump at once. Are you confused or nobody wants to speak? It's hard to tell. What do we think? What do we have? Are we going to shift towards the products? Or we're gonna find out on Wednesday. It's okay, suspense. Okay, that is it for now. We're gonna finish this on Wednesday because I can't keep track of time. Okay, have a wonderful day, everyone. These are posted on the Week at a Glance. Problem set 2, though, is posted with the key, so make sure you take a peek at that. That is your assignment for tomorrow, to learn the things.